Today, we are diving deep into one of the most incredible stories in all of technology, the battle for sight. We're going to explore how machines, against all odds, finally learned to see. We'll look at the shocking ways they've already blown past us, and also the profoundly human things that they still just can't quite grasp.
Our story actually starts way back over 2,000 years ago with Plato. He had this wild idea that our eyes weren't just passive receivers. He thought they were like flashlights actively shooting out eye beams to touch and feel the world. Now, of course, scientifically, that's totally wrong, but metaphorically, he was onto something huge. Vision isn't just about passively recording what's out there. It's an active, aggressive search for meaning. For most of history, we've kind of assumed our eyes are like perfect, high-definition cameras, right? Capturing the world in one beautiful, seamless panorama. But what if I told you that whole perception is really just a magnificent deception? That your own, seemingly flawless vision is actually a masterpiece of shortcuts, clever tricks, and some truly brutal data compression? So, over the next few minutes, we're going to tear down that illusion. We'll start with the biological blueprint inside our own heads, then see how engineers tried to copy it to build a digital eye. We'll be ringside for the grand tournament that pitted human against machine, explore the strange paradox of the AI's victory, and finally, look at the quest to give machines something like true, meaningful sight. Okay, let's start with one of the best-kept secrets of our own biology. Human vision isn't about seeing everything perfectly all at once. Nope. It's really a story about scarcity. It's a system that was brilliantly designed to handle a ridiculous amount of information with incredibly limited resources. So here's the first big secret. Try this. Hold your thumb out at arm's length. See the nail? That tiny area? That's the only part of your entire visual field that's in sharp, high-definition focus right now. It's a spot called the fovea. Everything else? It's just a low-resolution blur. So to create this illusion of a perfect picture, your eyes are constantly making these tiny jerky movements called saccades, about 3 times every single second, just painting that little high-res spot across the world. You're not watching a movie. Your brain is stitching together a rapid-fire slideshow to create your reality.
And let's talk about the raw data coming in. At any given moment, the retina at the back of your eye is getting bombarded by signals from 126 million photoreceptors. You can think of these as tiny biological pixels, all firing off information about light and color. I mean, that is a colossal stream of data. If your brain had to consciously process every single one of those signals, it would just melt. Evolution needed a much smarter and honestly a much more brutal solution.
And here's the brilliant solution evolution came up with. A massive data squeeze. The retina, which is actually a piece for the brain that kind of pushed its way into the eye, it acts like a preprocessor. It takes the signals from those 126 million photoreceptors and crushes them down to just 1 million signals that actually get sent to the brain. That is a 126-to-1 compression ratio. And it does this by basically ignoring all the boring stuff, the uniform areas, and prioritizing one thing above all else: edges, the lines where one thing stops and another thing starts.
Now, this biological blueprint, this whole idea of efficiency and abstraction, that became the direct inspiration for the digital eye. The big question for engineers was, how do you teach a machine to see using these same principles? Well, the answer turned out to be an architecture that is, in a lot of ways, the mathematical ghost of our own visual system. This is a convolutional neural network, a CNN for short, and it is the absolute workhorse of modern computer vision. And just like our retina, it doesn't try to swallow an entire image at once. Instead, it uses these little digital filters, you can think of them like stencils, that slide or convolve across the grid of pixels. And each one of these filters is designed to look for one very specific, simple pattern. And this whole process works in layers, building up in complexity. So the very first layer, it's like a sketch artist. Its little filters are just looking for super simple things: horizontal lines, vertical lines, basic contrasts, exactly how our retina prioritizes edges. Then the next layer acts like a sculptor. It takes those simple lines and starts combining them into more complex shapes and textures. Circles, squares, maybe the pattern on a car's grille. And then finally, the last layer becomes the master curator. It looks at this whole collection of shapes and says, okay, a circle here, another one there, with this specific texture, that's a wheel. And that wheel is part of a car. It builds understanding from the bottom all the way up.
All right, so we have our biological champion, the human eye, and we have our brand new digital challenger, the CNN. All that's left is to stage a competition. And that brings us to the main event, a grand tournament that would end up changing the field of AI forever. The arena for this competition was called ImageNet. It's this massive database, over 14 million images, all painstakingly labeled by hand. The task was pretty simple. Show an AI a picture and have it tell you what's in it. But the way they measured success was very specific. It's called the top 5 error rate. This means a guess was only counted as wrong if the correct label wasn't in the AI's top 5 predictions. So, for example, if the real picture is a beagle, the AI passes as long as beagle is somewhere in its top 5 guesses, even if its number 1 guess was something else, like hound.
In the early days, progress was, okay. In 2010, the best models had an error rate of about 28%. A year later, it crept down to 26%. The progress was there, it was incremental, respectable, but it wasn't a revolution. And then, 2012 happened. A brand new kind of model, a deep convolutional neural network named ImageNet, entered the competition. And it didn't just win, it absolutely shattered the field.
So to understand just how huge this was, you need to know that researchers had already tested humans on the same task. And it turns out the average person has an error rate of about 5.1%. ImageNet, back in 2012, came in at 15.3%. So still a ways to go, but it was such a massive leap forward that it kicked off the entire deep learning revolution. And then, just 3 years later, in 2015, AI models officially crossed the human threshold, achieving an error rate of just 3.6%. For the very first time, a machine was better at this one specific task than a person was. The machine had won the grand tournament.
But this victory, it wasn't the end of the story. Not at all. In fact, it revealed this deep and totally fascinating paradox. By winning, the machine showed us exactly where it comes up short. It exposed this massive gap between just identifying things and truly understanding them.
And you can see this paradox perfectly in the way that humans and AI fail at vision. It turns out our failure modes are perfect mirror images of each other. We humans, we are brilliant at high-level context. You walk into a room, you instantly know, oh, this is a birthday party. But if you showed most of us pictures of 120 different dog breeds, we'd be terrible at telling a whippet from an Italian greyhound. The machine is the dead opposite. It excels at that fine-grained detail. It can classify those 120 dog breeds with near-perfect accuracy. But its failure? A complete and total lack of context.
This is the absolute heart of what we call the context gap. The AI sees the pixels that make up a dog and a party hat and a cake, and it can label each of those objects one by one. But it doesn't get the semantic relationship, the meaning that connects them all. It can't grasp the big picture, that social ritual that we call a birthday party. Basically, it identifies all the nouns, but it completely misses the story. And if you miss the story, you can't really interpret the scene.
So this context gap, this is the new frontier in AI research. How are engineers trying to close it? Well, let's take a look at the really advanced tech being built right now to give machines something much closer to true understanding, or what some people are starting to call semantic sight.
Okay, so the first step was to teach the machine to pay attention like we do. Remember the Fovea, that tiny high-res window? AI is now using something called attention mechanisms to do the same thing. The first kind is called hard attention. This is a lot like our saccades. The model literally crops a small thumbnail out of the image to analyze, and it just ignores everything else. The second kind is soft attention, which is more like our mental focus. It looks at the whole picture, but it applies a sort of heat map of importance, paying way more attention to the pixels of a person's face, for example, while giving less weight to a blurry background.
But just paying attention isn't enough. The real breakthrough right now is in something called multimodality. It's a fancy word, but it just means connecting different kinds of data, like, say, sight and language. A model called CLIP does exactly this. It learns about our world by looking at billions of images and the text captions that people wrote for them online. And by doing that, it starts to learn the relationship between what pixels look like and what concepts mean. This lets it understand totally new ideas it's never been explicitly trained on. You can ask it to find a photo of a dog in a tuxedo, and it can actually put together its visual knowledge of dog with its language knowledge of tuxedo to find it. This is how we're starting to bridge that context gap.
So after this whole journey, from ancient Greek myths to modern neural nets, where do we actually stand? Let's wrap this all up with the final battle card, a side-by-side comparison of these two amazing but fundamentally different ways of seeing the world.
I mean, the parallels here are pretty striking, right? Our biological rods and cones are mirrored by digital pixels and RGB channels. Our physical and mental attention has its digital counterparts in hard and soft attention. But that core difference is still there. Our greatest strength is that high-level, big-picture reasoning.
The machine's strength is its totally superhuman ability to pick out fine-grained details. And our weaknesses? They're simply the mirror image of each other.
We've come such a long way from Plato's mythical eye beams. We've taken apart our own sight and built a digital copy that can, in some ways, outperform us. But the ultimate challenge is still out there. As we get closer and closer to bridging that context gap, we're left with one final, and I think profound question. Will a machine ever be able to look at a human face and not just identify its features, but truly understand the story, the emotions, and the complex consciousness behind the eyes? That is the final frontier in the battle for sight.